is Euclid digging the dark in the Planck universe.
Okay, good morning. Thank you for inviting Euclid at this fantastic Planck conference. With Isabelle Grenier, you move from low energy photons to very high energy. Now we are going to move from past and present to the future with this Euclid mission, which will try to dig the dark universe, in particular using the most recent result obtained by Euclid. By Planck, sorry. So one thing which is first reassuring from Planck is that even if you have decreased a bit the amount of dark energy, you have still a huge fraction which is dominating the dynamics of the universe, which is good for us. And when it is combined with the result of the type 1a supernovae in particular, for which the acceleration of the universe is now demonstrated at a 99.999% confidence level, the key question for the future, which is beyond the scope of the Planck mission, is what is this? Why the universe is accelerating? What could be the nature of dark energy, if it is dark energy, pure dark energy, or something related to modified gravity, or something else. We would like also to explore when occurs the transition between the matter energy dominated universe and the dark energy dominated universe, and what could be the impact of our knowledge on the dark energy properties on fundamental physics and post-Planck cosmology. So the Euclid space mission is an ESA mission selected in 2011, which was adopted last year. And the aim of this mission is to understand the origin of the accelerating expansion of the universe, trying to understand the properties of the dark and the nature of dark energy, generically dark energy, which is responsible of the acceleration of the universe, and trying to distinguish the options to explain the origin of this accelerating universe by designing a mission which has several independent but complementary cosmological probes in order to track signature that could come from modified gravity or dark energy or something else, by observing the geometry of the universe and the expansion history of the universe on one hand, using gravitational lensing and galaxy clustering, and on the other, to explore the property and the cosmic history of structure formation using wake lensing, redshift space distortion, and clusters of galaxies. And one of the key elements of this mission, this is why it is a space mission, and because in particular we are going to observe weak gravitational lensing generated by the large-scale structure of the universe, is to control the systematics to a very high level of accuracy, which I think is the most difficult point of gravitational lensing, in particular cosmic shear. So, in order to design that mission, we need to set some constraints on some goals, some objectives to that mission in terms of accuracy. So, assuming that we parameterize the ignorance we have on dark energy by this equation of state, which depends on look-back time here, or by parameterizing the growth rate of structure as follows, depending on the gamma parameter, which could be a parameter to constrain, modify gravity model, which is here taken not as the way we are going to do that ultimately, but in order to set, some constraint on that number in order to explore which accuracy we need on that parameter. Then now, if you go back to the most recent result obtained by Planck, in particular on W, on the constant term and the first term that may depend on time, you see that we are still compatible with a value of -1. We are still compatible with a constant value, but Planck really leave open option to have a W term which is different from -1, or which may vary with time. And this is exactly one of the main goals of the Euclid mission. So this this plot in particular is really very interesting for us. So Planck did not explore the gamma parameter in the first paper, so I have no equivalent to show for gamma, but sure that we will have this late in the future. So now, if we want to translate this in terms of accuracy for the mission itself, what we want is first to distinguish a lambda option to a dynamical dark energy model, which means that we want to slice the universe in order to explore to explore the evolution of a structure and the expansion rate as function of redshift. And the objectives we have is to get, using Planck data alone, without Planck, to get a figure of merit of about 400. That means that if we have a figure of merit higher than 400, then the fact that we measure something which is close to -1, which would favor a lambda model, would be a strong case for lambda with odds of more than 100/1. So this is what we call a decisive evidence here in our own wording. And you see that now, if you use Planck together with Euclid, then instead of having a figure of merit of 400, we will be about 10 times higher, and an accuracy on these two parameters, which is now at a % level. So we also explore what could be the accuracy we may need on gamma, assuming that the growth rate of structure can be parameterized with this gamma parameter. And in that case, the precision we need on gamma is about 2%. So the design of the mission of Euclid, of the Euclid mission, has been organized around these goals. So the probes that we are going to use for Euclid are first the baryon acoustic oscillation for the geometry of the universe and the expansion rate, and the redshift space distortion for the growth rate of structure in particular. And the mission itself will get 50 million spectroscopic redshift to a 10 to -3 accuracy times 1 plus z, over 15,000 square degrees of the sky. That is a full sky, but the ecliptic plane and the galactic plane. So with these 50 million spectroscopic redshift, we will be in position to explore the BAO and RSD in the redshift domain between 0.7 to 2. Now, together with the redshift surveys, Euclid will have also a dedicated cosmic shear surveys, which will measure the shapes of galaxies in order to measure the gravitational shear produced by the large-scale structure of the universe. And this will be done as function of look-back time by slicing the universe with about 10 different slices between redshift 0 and 2. And possibly by reconstructing the 3D power spectrum as it has been recently proposed by Kitching et al. In particular, the paper that you have used in the Planck data. So in principle, we will be able to explore the CL as function of redshift and compare to a series of dark energy model to see how far we can go in the constraint on dark energy. And the Euclid mission will measure the shapes of galaxies of 1.5 billion galaxies over 15,000 square degrees. And as you know, when you want to use gravitational lensing, because you scale as function of angular distances, and also because you are contaminated by the intrinsic alignment, it is very important to decontaminate and get a rough estimate of this redshift using photometric redshift. Spectroscopic redshift are not necessary, but photometric redshift over 1 billion galaxies or so is necessary. So in order to do that, and because we are going to explore this redshift range, it is unavoidable to use jointly optical and near-infrared data together for the photometric redshift. And in addition to that, you need also to calibrate those redshifts in the magnitude range of galaxies you are using to measure weak lensing. This is why, in addition to spectroscopy, we will also have near-infrared photometry done with the Euclid mission, because we will be roughly 1,000 times more efficient than any ground-based dedicated telescope to near-infrared observations. So in that case, we will use 3 near-infrared bands with Euclid, Y, J, and H, together with 4 optical bands that will be obtained from the ground-based surveys, which are currently running in the south or in the north, or which are already planned for the future. So together with that, we will also have, basically for free, because we will have the imaging and the spectroscopy, a huge sample of clusters of galaxies. We will have about 60,000 clusters between redshift point 2 to 2, out of which 10,000 will be at redshift higher than 1. And in addition, among those clusters, 5,000 clusters are expected to have a giant gravitational arc. So in addition to the weak lensing mass reconstruction, we will be able to constrain the mass together with a strong lensing effect, since we will have the giant arcs and the redshift of those arcs. So that means that we will be able to have a huge sample, optically selected but homogeneous over the sky, together with a sample of gravitational arc for which weak plus strong weak lensing mass reconstruction will allow us to have a fairly accurate mass maps of these clusters. So, of course, it is for us an option, ideal case to have a synergy with Planck, in particular for the integrated Sachs-Wolf effect, and a synergy also with the Rosita satellite that will provide X-ray clusters of galaxies that we can combine together with this data. And of these data, of course, the primary goal will be to observe any deviation from any standard, let's say, standard dark energy model we may have. So now, together with these probes, we can design the mission, provided we are able to set constraints on the parameters we want to measure. And since we are going to observe a huge sample, we need to cover the whole extragalactic sky. And we have fairly hard requirements on the shape measurement of the galaxies in order to measure the gravitational shear produced by the large-scale structure of the universe with a fairly high accuracy. So these parameters have been set in order to meet the requirements. And we know from present days simulations of weak lensing analysis that this is within the range, within the reach of next generation shape measurement tools we may have for weak lensing. Together with this wide survey, we will also have a deep survey that will cover 4 square degrees, which will be primarily used for calibration of the instrument, shape measurement, and redshift. But it will be also used in order to do legacy science, 2 magnitude fainter than the current wide field survey, which is expected so far. And here you also have, in addition to this requirement for the shape measurement, also requirement for the spectroscopic sample in terms of completeness, purity, and confusions. And these requirements on confusions come from the fact that the spectroscopy will be done on a slitless mode. So we don't have slits, so we will have overlaps between spectra. And because of that, we have to be sure that we have a well-designed survey that allows us to separate the spectra even when we have contamination due to overlap of galaxies, overlap of spectra of galaxies. So the current mission can be summarized in this table. It will be a 6-year survey covering 15,000 square degrees on one hand and 40 square degrees on the other, with 2 instruments, a visible wide field imager with a very broadband filter that will be used for the shape measurement of the galaxies and cosmic shear. And on the other, we will have a near-infrared photometry in 3 bands, and together slitless spectroscopy in the infrared. So the 2 instruments will work in parallel, partly for the spectroscopy and visible, and the photometry will be done sequentially. So this is the baseline, and together with that, we are also exploring other options that could be added on to the surveys themselves, to the dark energy survey itself. In particular, whether we could do type 1a supernovae, whether we could do microlensing in the galactic plane in order for the analysis of exoplanets, or possibly a sky coverage of the Milky Way that could complement the data obtained for the Gaia mission. So the observing strategy will be as follows. We will basically, for the wide survey, we will spend about 1 hour, a bit more than 1 hour per target, per field. And each field will have 4 observations in a dithered mode with a small dither of few arcseconds. And during one exposure, we will do in parallel the VIS deep imaging for shape measurement with the slitless spectroscopy. Once we will have one exposure in VIS and one in slitless spectroscopy, we will move to the 3-band near-infrared photometry. And once it is finished, we dither a bit, and we start 4 times in order to have in total 4,500 second long sequence per field. So the instrument itself will be the telescope will be a 1.2 Korsch telescope and astigmat in order to have a very wide field, almost flat, which is important for the wide field imaging capability we need for weak lensing. And the telescope itself will be built by Astrium, which was selected in December. The mirror itself will be in SICK. This is the current design of Astrium, and below, underneath this mirror, you will have the instrument that you can see here, that I zoom here. You see the VIS imager here. You have a dichroic here, and here the near-infrared imaging and spectrograph instrument. So, and you see the stability we need in order to get the shape measurement with a fairly high accuracy, not contaminated by stabilization problem. The 2 instruments will have a common field of view of about half a degree. The VIS instrument itself will have 36 4K by 4K E2V CCDs with a pixel size of 0.1 micron. It's quite a big camera, not as big as Gaia, but probably one of it should be the second biggest. So it's a big, really big wide field instrument that will be mounted. And the instrument itself is not incredibly complex as compared to what you have experienced with Planck and Herschel, I believe, but it has to be done anyway, in particular in terms of stability. Now for the VIS instrument itself, it's a focal reducer that includes 2 a filter wheel and a Grism wheel. Here you will have 16 near-infrared detectors, and the field of view will be 0.5 degree and a pixel size of 0.3 arcsecond per pixel. And we will have 4 Grism, 2 in the blue and 2 in the red, and 2 Grism will be vertically oriented and 2 other horizontally oriented, so that we will have a sequence of exposure where we will have spectra which will be perpendicular each other, so that we will be able to separate the to measure and avoid the contamination of spectra produced by the fact that we are doing slitless spectroscopy. So this instrument is more complex than the VIS instrument. This focal reducer is about 1 to 1.2 meter long, so it's not a small instrument. And of course, he has also a huge mosaic of detectors on the focal plane, which is also a quite difficult part of the instrument. So the consequence of these 2 instruments in terms of data volume here that we expect for the 2, and the fact also that we are going to extract spectra which overlap each other on one hand, and also because we will have to measure the shape of galaxies for cosmic shear, mean that the data processing is a full part of this mission, as it has been for Planck. So This is a really significant part of the contribution of the countries to that mission, the ground segment, the science ground segment, because we are going to have a huge volume of data, heterogeneous set of data, because we will have ground-based data and space-based data. We will have imaging, morphometry, photometry, and spectroscopy to handle. And about 20 to 30 petabytes of data, corresponding to roughly 10 billion sources up to sigma higher than 3 for all galaxies. So it's a really important part of that mission, also for the shape measurement, which is critical for this kind of mission. So if everything goes well, we will launch this telescope by 2020, and we expect to have the first release of the data 26 months after the launch, the beginning of the survey. Now, in terms of performance, here you can have simulated images of what we expect on the VIS instrument. It's a 2K by 2K E2V simulation. You see the cosmic rays, and you see also a small trail, vertical trail on this image. It's because slowly the images will be degraded by cosmic rays. So it is also a source of contamination for the weak lensing signal. So we had to demonstrate during the selection that we'll be able to handle that and correct the CTI, charge transfer inefficiency, sufficiently accuracy in order to keep the performance as required. So this has been demonstrated, and in the worst case scenario, that means assuming that all the data were obtained at the end of life of the instrument, and the CTI corresponding to the worst case when you are far from the readout of the detectors. And this is what we had to do in order to demonstrate the feasibility of that mission. Now, in terms of image quality we expect, here it is a simulation of M51 as it could be seen by the VIS instrument if M51 were at redshift 0.1 as compared to what would observe the Sloan. And now if this M51 is located at redshift 0.7. So you see that in terms of image quality, this is exactly what we expect for the shape measurement. But you see also that this imager that will cover 15,000 square degrees will correspond to a Sloan, a super Sloan sky survey, but at redshift 1 instead of at very low redshift. So it's a continuation, a next generation Sloan surveys, and the important legacy part of the Euclid mission is really well described by this kind of image quality you can expect. Another example of the image quality, here what we have done is that we have extracted from the CFH-TLS some giant arc observed in the real images, and then we have used this, the model, the lens model of this in order to do a model or a lens model of images that could be observed with the VIS imager, the Euclid VIS imager, and what will observe Euclid in the near infrared. And you see that for some of them, the difference between the ground-based data, even obtained at CFHT with a seeing of 0.6 arcsecond, as compared to the VIS, is quite spectacular, which is also another legacy aspect of that mission. Now, regarding the performance in power spectrum recovery, so the simulation is done assuming that we have covered 15,000 square degrees in 5 years. And the patches you see here show the sequence of observation over the 6 years. And here, this is the objective we have. In that range, we want to recover the dark matter power spectrum to 1% accuracy. And we have demonstrated that using this survey and the simulated data of the VIS instrument. Now for the near-infrared spectroscopy and near-infrared imaging, these are images from the VIS near-infrared photometry, and these are the same image but now with in a slitless, by putting the grism in the path. And you see now all the spectra, and you see that the spectra may overlap a lot. So it's really important to have the 4 spectra per image in order to extract the signal. So whether it is feasible or not to get the redshift accuracy when you have a slitless mode has been demonstrated, and this is what you see here. The black dot shows the position, the true position of the galaxy in the simulation, and the red dot, what has been recovered using this kind of extraction of spectra. And you see that we are still, for all these galaxies, within the range of the requirement. Now, in terms of power spectrum for the galaxy, this is also an estimation of the performance using simulated data. I think it corresponds to 20% of the whole data set obtained with Euclid. So you see the difference between the Sloan and Euclid, and how it could compare to some dark energy model we may explore. Now, regarding the growth rate, a simulation has been done in particular within the range of exploration of Euclid between 0.7 and 2. And you see here, the error bars expected using Euclid data between 0.7 and 2. And for 3 estimates of the statistical error on the number of galaxies that may be available. So the requirement is black, the center one, and the blue, in particular the orange here, is if we don't meet the requirement, we lose half of the galaxies for any reason. So you see that in terms of accuracy and performance, we are well within the requirement of that mission, and this plot shows something which is quite spectacular. And these data, which are shown here, are only using the spectra. We don't use together the weak lensing data of Euclid, nor the Planck data. Now, if we use the Planck data together, this is what you could obtain in terms of precision for the dark energy model. So weak lensing and galaxy clustering, we will reach about 2% for the constant term and 15% for the first term that may depend on times. Now, if you use Planck and Euclid, you are below 1% and below the 5% goal requirement I described before. So you see that the joint analysis of the 5 probes of Euclid together with Planck data is really within the reach of what we would like to do in the future with Euclid. Now, in addition to that, we also have, again, the legacy value of this project, and in particular, in terms of gravitational arcs and Einstein rings around clusters of galaxies, but also around galaxies. And we expect about 300,000 such strong lenses case around galaxies. So this is what you get with the current SLAC surveys, which has been done with the Hubble Space Telescope. And this is what you will get after 2 months with Euclid, and we have 66 months planned. So you see that the legacy value in terms of exploring galaxies using strong lensing effect is also quite spectacular. Now, regarding the organization of this mission, I have 1 minute, okay? So we have industry ESA, which is leading that project. It's an ESA mission, of course. And we have a consortium which has been built in order to build the instrument, and which is responsible for the data processing and scientific exploitation of this mission. We have, for the moment, about 1,100 members in more than 100 laboratories, most of them in Europe. And also NASA is now contributing to that mission. So you see, it's a really big consortium, and probably in the lesson learned, we certainly have to learn from Planck how you manage such a big group, because it's a bit worrisome, I would say. Now, regarding the schedule, so we are here. The payload has been selected in December. The service module will be selected by by June. And then the PDR for the instrument is expected by beginning of 2014. The PDR of the PLM a bit later in April 2014, and the satellite PDR in 2014 as well. And this is the ground segment PDR is expected a bit later. We have a shift with respect to the instrument 2 years later. And if everything goes well, we expect to have the first pipeline Model 0 running by 2017 in order to get operational 1 year before the launch of the mission. And if everything goes well, Euclid will be launched by beginning of 2020. So in summary, this mission is so far the only space mission selected and totally dedicated to the exploration of the property of the origin of the acceleration of the universe, whatever it is. This mission will have 5 cosmological probes: wake lensing, redshift space distortion, baryon acoustic oscillation, clusters of galaxies, and integrated Sachs-Wolf effect, which is, I think, a fantastic mission for Europe and for Europeans, astronomers and physicists. But we also have a huge legacy value of this mission, and I think it is important when you have planned mission for 10 years, you never know what will happen to your goal. So it is important to keep a very important aspect of this mission, to keep in mind that it has also a huge legacy value. So we expect 12 billion galaxies observed up to signal-to-noise 3, 50 million redshift. We also guess that it will be a huge reservoir of targets for the other facilities, next-generation facilities. It is also a chance for all the young scientists to have this kind of mission in perspective for their future, and for the physicists and astrophysicists for the next 20 years. And of course, we hope that we will do as well as you did. And thank you in particular for all the spectacular results you obtained.
Thank you very much. Time for 1 or 2 questions? Yeah.
So, as you said, you have a rather demanding stability on the pointing. You require 25 milliarc seconds over 700 seconds, right?
Yes. Mm-hmm.
Now, I'm sure you don't have yet the solution, the technical solution, but you're studying a number of solutions.
Yeah.
What happens? The question is the following: what happens if you have to release that requirement?
So in the risk analysis we have done, we have, first of all, for the moment, the proposals we have meet these requirements. So and it is not considered as extremely hard to reach. Okay, so we cannot assess that it will be a huge risk for the mission. Second, we have done an exploration, a risk analysis of what could be the parameters if we degrade that stability by a factor of 2, and we still meet the requirements. So that means we are safe in the 2 sides, in terms of risk analysis, and on the other side, in terms of the responses we got from industry.
Okay, maybe one other question? Yeah, okay. I think it was Charles we wanted to get to.
We'll squeeze 2 in. We'll squeeze 2 questions.
Could you say a bit about how you'll handle the issue of the changing point spread function across the band passes?
Across the?
You have wide band passes, and the point spread function is a function of wavelength, and you have to characterize the point spread function very accurately. So
that's correct.
How will you deal with that issue?
For the moment, we have modeled this point spread function, not over the whole filters itself. Okay, so we have modeled the PSF at several points of this filter, and for the moment we have the stability and the accuracy we need for the PSF. So in principle, is not an issue. What could be an issue is a chromatic effect of the PSF or the galaxies we are measuring. And this aspect has been explored, in particular from the science working group dealing with weak lensing. And we know how to deal with that because we will have the information, the color information of the stars and galaxies, because we will have optical and also near-infrared data. So we can control these systematics and take this into account. So in principle, even if it is a very broadband filter, it's no longer an issue. It was an issue, something that we had to check and double check, and it has been done.
Okay, so we said we'd squeeze in one more question, so.
So by the time Euclid flies, there should be maps of several thousand square degrees with high signal to noise of the CMB polarization. So these should give shear maps with a 1 arc-minute resolution of roughly the same angle. So of course there's an advantage here. You know exactly what the source redshift is, and the systematics are completely different. So how useful will these be for calibrating Euclid, and what's the comparative figure of merit that you get if you
I don't think we have never done that to compare, the figure of merit of this polarization with respect to weak lensing. So I cannot answer directly to your question. I don't know whether Tom or Hank have explored that. I think it's not done yet. This is something we have to do anyway. What is really important here is that we will have the redshift of all the sources. So we will have the slices, which I think is really what we want to do, in particular recovering the 3D power spectrum. So there will be complementary, but I cannot provide exactly the details to that question. We can discuss this with Tom probably later.
Okay, let's thank Yannick again.